Okay, so we've seen that kurtosis of a statistic measures the thickness of what? Of the tail in comparison or in relation to the what? To the tails of that is of a normal distribution. Okay, we are saying that if that is okay, for a normal distribution or for the perfect normal distribution, we have a kurtosis of 3. So in case in our computation or in our in our distribution, we get a kurtosis which is less than 3 which is less than 3, then it means our tails will be thinner in relation to the what? To the tails of the perfect normal distribution. Okay. What about if the kurtosis is greater than 3? So if the kurtosis is greater than 3, then we are going to say that we have thicker tails or fat tails, okay, in comparison to what? To the perfect normal distribution. Okay, let's see what the notes that is are saying. That is the normal distribution has a kurtosis of 3, which indicates the distribution as neither fat or thin tails. That is, a kurtosis of 3 means that we have neither fat nor that is thin tails. Like we have a standard what? Standard tails. Okay, that is a standard uh, thinness or thickness of what? Of the tails. Okay. Therefore, if we observe or if we have or we if an observed distribution has a kurtosis greater than 3, then the distribution is said to have heavy tails when compared to what? To a normal distribution. Okay, that is heavy tails meaning thicker tails or fat tails. Okay, but if the distribution has a kurtosis of less than 3, okay, of less than 3, then it is said to have what? Thin tails, okay, when compared to what? When compared to normal distribution. Okay, let's try and check maybe more illustration on that is on kurtosis. Okay, that is kurtosis of a distribution of a distribution. Okay, so when we are talking about kurtosis, what are we talking that is of? Okay, when we are talking about kurtosis, so basically we are saying that kurtosis is measure of whether the data are heavy tailed or that is light tailed. That is the heaviness. We are talking about the thickness of the tail. Like for example, let's assume we have these two different distributions. Okay, of course it follows a normal distribution, and also we have another distribution which has thin what? Thin tails compared to what? To the that is to our normal perfect normal distribution. Okay, so you can see the thickness of the tail. Okay, the thickness of the tail here, it's small, okay, in comparison to what? To the standard normal distribution or to the perfect normal distribution. So in this case, kurtosis here, kurtosis is equals to 3. In this case, kurtosis will be, what will it be? Someone in this that is tail with the that is with a very lost thickness. What will it be? Someone? Someone? Neither. Okay. Any. not really. For the standard, okay, you can see for the standard or for the perfect normal distribution, the tails are neither thin or thick. Okay, that's why we are having a kurtosis of what? Of 3. But on this illustration, let me say we have A and B. So in this B, you can see the thickness of the tail, okay, is what? The thickness of the tail, it's all the tails are thicker than that of a perfect normal distribution. What does then mean? Okay, kaka 0, not really, that's not a 0, but okay. For Michael, yes, that is Michael, you got it. That is for this for illustration B. Then any for illustration A is greater than it means that is the kurtosis. It's greater than what? Than 3. Yes, very correct. So for this case, kurtosis will be greater than 3. Okay, and for this case, kurtosis will be what? Will be less than what? That is will be less than 3. Okay. Yes, let's continue. Okay, so we were checking on this. That is sets with high kurtosis tend to have heavy tails or outliers. Okay, so you can see that the one with heavy tails, okay, it has outliers or it has many outliers. Okay, then data set with low kurtosis tend to have light tails or lack the what? Lack outliers. Okay, so what can we say with this? We can say that that is the data on this distribution have what? Have many outliers. Okay, it has many outliers. But for the one with the thin tails, okay, than the normal distribution, has what? Has very less outliers. Okay, it's like even maybe if we were to give an example of the what? Of the height, okay, height of people in the what? In the class. Let's assume maybe the standard height is 150 centimeters. Okay, so you'll find we have some people here. Okay, some people here with the height of that is with the height of 60 centimeters. Okay, 60 centimeters. We'll also find also a high number, okay, of people here with what? With that is a range of 180 centimeters. That is, this is the height, okay, like 1.8 meters. Okay, so compared now to here, when now we come to this other all to the second that is the illustration, if we try to plot, you will find that we have very few. Okay, we have very few people with maybe 50, with a height of 50 to 60 centimeters, and we'll also find few people here with height of 180 to 200 what? Centimeters. Okay, so meaning you can see if we are having thicker tails, so meaning we'll have more distribution or data points here, okay, compared to when we have what? A thin tail. That's why we are saying that that is for data set with high kurtosis tends to have that is heavy tails or many outliers. Data set with low kurtosis tend to have what? light tails or lack outliers. Okay. Yes, so that's a perfect example, in fact. Okay, that's a perfect example. Then remember, I also told you about that is the peakness. Okay, the peakness and the that is the peakness of the what of the distribution. Remember, I said the tail depends with what, with the peak of the tail. Why? Because if maybe we have that is a high peak distribution, then definitely the tails will be what, will be thicker, okay, compared to that of what, to that of that is to that of a normal distribution. Let's maybe have a look on that. Okay, so kurtosis, we've said, is a measure of tailedness of a distribution. The tailedness is how often outliers do what, occur. When we are talking about tails, okay, the thickness and the thinness of a tail, it's like we are discussing about what? It's like we are discussing about the outliers we are having, okay, in that data. So if maybe the tail is thin, then it means we have less outliers. Okay. Either remember, outliers, we said it's any extreme high or extreme low value. Okay, all small value. Okay. Yes. So excess kurtosis. Okay. Excess kurtosis is the tailness of a distribution relative to normal distribution. Okay, relative to normal distribution. So let's start with this. So the distribution with minimum kurtosis or medium tails meaning we are talking about almost a perfect normal distribution. Okay, so we are talking of medium tail. Okay, so distribution with medium kurtosis, meaning we have a medium number of outliers, are called that is mesokartic. Okay, mesokartic. Then when we are talking about that is kurtosis with thin tails, okay, we are talking about what, that is platycartic. Okay, then when we are talking about a distribution with high kurtosis or fat tails, then we are talking of leptocartic. Okay, and you can see the clear that is distribution here. Let's assume mesocartic, its distribution, it's our what? It's our perfect normal distribution. Okay, if it is our perfect normal distribution, okay, then we'll say that a perfect normal distribution that is displays or as what we call mesocartic distribution. Okay, when it comes to the what, when it comes to the that is kurtosis. Okay, then if we increase the standard deviation, okay, I will show you majorly this kurtosis is affected by one factor, that is standard deviation. Okay, when we change the standard deviation, this is how the normal distribution will behave. When we change, maybe we change or we regulate or control the normal distribution with mean, then the curves will be of the same shape, but now it will be located maybe to the right or to the left of the what, to the left of the that is of the normal distribution. Okay, right. So we've now talked about these three types of kurtosis. Okay, so if maybe you need to read more about it, you can go and search more about it that is about kurtosis. Okay, we have these types, okay, and we have some properties of the same. Okay, I will share this link. Okay, can see it's a good link. I'll share this link, and maybe you will be able to learn more about these types of what? Of kurtosis. My objective was just to show you that is the kurtosis. What do we mean by the term kurtosis? Okay, so then with that we came across now these types of kurtosis. Okay, that is kurtosis with medium with medium thinness or thickness of a tail, with also thinness of a tail or a thin tail, and with that is thicker tails or heavy tails. Okay, you can go and read more of the more of the properties here, so you can see we say that for a perfect normal distribution is what? Mesokartic. Okay, and here it is. You can see that is a normal distribution has a kurtosis of 3. So any distribution with a kurtosis of approximate 3 is what? It's mesokartic. Okay, what about maybe the one with what? The one with less than 3. Okay, so for that is platykartic. Okay, we are saying that a kurtosis of less than 3 and excess kurtosis of less than what? Less 0. So anything less than 3, we talk about what? Thicker tails. Okay, we talk about, is it? No, we talk about, yes, we talk about thicker tails. Okay, is it less? No, we talk about thinner tails. Yes, we talk about thinner tails, which is this one. Okay, but that is leptokartic. Then we are talking about that is kurtosis is greater than what? The kurtosis is more than 3. Okay, all right, good. Any question up to that point? Any question about kurtosis? I will share. Okay, all good, Michael. Thank you. What about the others? What about the others? Understood? Okay, Dennis, Kennedy, nice. Miss Mary, Eric Otieno, good. Aini means we are all good. Thank you, thank you. So let me just share this link. It might help you. Okay, let me try and see if I can share it over WhatsApp. Okay, then I guess we are good with kurtosis. Now we are going to normal distribution. Okay, good. I can share it here first. I will also share that is the link over WhatsApp. Good. Now let's continue with our with our first distribution. Okay. Our first distribution, we've been discussing much about normal distribution. Okay, everything in reference to what? To normal distribution. And why is it so? Because normal distribution is almostly applicable in any area, okay, or field of study. Okay, we live with what? We live with normal distribution. Like even in this class, if I give you a test, okay, if I give you a test, definitely it will follow what? It will follow a normal distribution. That is, we will have few scoring high, that is high scores, we'll also have most of the students scoring averagely, and then we'll still have a few students scoring that is low points, or that is a low scores. Okay, definitely that will follow a normal distribution. Or if we were to collect data in terms of weight, okay, or in terms of height, or in terms of that is the arm length, okay, definitely that data will what? Will follow a normal distribution. Remember also, I also say that normal distribution is also known as a Gaussian distribution, or bell-shaped what? Bell-shaped distribution. Good. Now, that is in the probability theory and statistics, the normal distribution is also known as Gaussian distribution. Is the most significant continuous distribution. So we have one property. This is a type of what? A normal distribution is a type of continuous distribution. Okay, meaning it will be represented by what? By a curve. Okay, it will be represented by a curve, and its equation, let me try if I can remember. If maybe I can remember, please feel free to also help me. Okay, so I can remember that for that is this is the equation of a normal distribution. That is 1 divided by is it 2 square root of pi, okay, multiplied by exponent of negative mu minus that is into, that is half, either you can that is raised to negative half, or we can just keep it this way. We can just say that is mu minus, is it x bar, into squared, divide by what? Divide by 2. Okay, can't remember well. Let me just confirm, not to lie to you. It's better to confirm than lie. Equation of normal distribution. All right. Yes, I guess I missed this part. And here. Okay, so let me just write it well. So it is it is 1 divided by 2 sigma square root of, or let me just take that is the formula here. Let me just copy the formula here. It should be easy. So this is the normal distribution formula. Okay, that is 1 divided by the standard deviation, that is multiplied by square root of 2 pi, that is multiplied by exponent of negative half into the xi's minus mu, divided by that is standard deviation, all that squared. Okay, yes, so this is the formula for normal distribution. Okay, no need to cram it. Okay, it's always available, and I don't think if it can be tested. So sometimes we are saying that sometimes it is also called as or known as a bell curve. Okay, a large number of random variables are either nearly or exactly represented by what? By normal distribution. In every physical science and economics. Okay? Yes. Furthermore, it can be used to approximate other probabilities distributions. Therefore, supporting the usage of the word normal is about the one mostly used. Okay? As in about the one mostly used. So let's maybe go or jump into properties of that is of a normal distribution. I've given you maybe already that is some of real life examples of what normal distribution. Okay, like the way maybe the weight of students in a class are distributed, also the height of students in class, okay, also the cut scores, with and very many examples. Okay, so remember we say that in a normal distribution, mean, median, and mode are equal. Remember this. And trust you me, you'll be asked about this property. Okay? You'll be asked about this property. Maybe which is the distribution where mean is equal to median is equal to mode. Okay, or which is the distribution where mean, median, and mode is equal. Trust you me, you won't miss that. Then we have the total area and the under the curve should be equal to what? To 1. That is the total area under this curve. So I'm talking of this part up to this part, where maybe the tail ends. Okay, the total area under the curve is what? Is equal to 1. Yes, I remember that is we learned this back in what? Back in high school. Okay? Yes. Then the other one, the normally distributed curve should be symmetric at the center. Okay, that is the normal distribution should be symmetric in that is in center. Or and also if in such a way, if we draw a line where we have the peak, it should cut these two that is it should cut that is the distribution into two equal parts. Okay, yes. So there should be exactly half of the values, or there should be exactly half of the values are to the right of the sender, and exactly half of the values to the left of the sender. Yes, this is what I mean. Like all the values here and all the values here should be what? Should be equal to each other. Okay, like exactly half of the what? Like half of the values used to plot this distribution are on the left, and then the half of the other values are to the what? Are in the left of the curve. Okay. The normal distribution should be defined by the mean and standard that is by and standard deviation. Yes, very correct. Because when we define normal distribution, we usually say that a data set is normally distributed with mean mu and standard deviation sigma. Okay, and then for a standard normal distribution, we usually say that is a data set. All values are standard normally distributed with mean 0 and standard deviation 1. Okay? Yes, this is how we define a standard normal distribution. And we are saying that the normal distribution should have a defined mean and a defined standard deviation. Then the normal distribution curve must have only one peak. Like it should only have one peak, not two peaks. Like in this maybe distribution, you might have a such distribution. Okay, so you can see this one as 2 peaks, so this can't be that is a normal distribution. Okay, otherwise for a normal distribution we only have one curve. Okay, we only have only one peak, or one peak on that is on the curve. Okay, then we have the curve approaches the x-axis. The curve approaches the x-axis, but it never touches what? It never touches, or it extends, it extends further away from the what? Away from the mean. Yes, for a normal distribution, you won't have this kind of maybe this that is a tail. The tail won't touch what? Won't touch the that is the x-axis. Okay, it won't touch the x-axis. Instead, it will run till maybe it will appear to maybe to touch the x-axis, but it won't. Okay, at any point touch the x-axis. Okay. Yes. Then we have some applications. So the application, the normal distribution, all the normal distributions are closely associated with many such things as marks of a scored test, yes. Height of different person, yes, I have talked about that. Size of objects produced by the what? By a machine, and also the blood, that is patient's blood pressure. Okay, like Kennedy, if maybe you are doing a research and you have that is a data of all your patients with high blood pressure, okay, or with blood pressure, definitely you will come up with that is a curve. If you plot that data, you will come that is across, or you will come that is to this kind of normal distribution. Okay, all your data will tend to follow normal distribution. All right, all right, good. We usually have frequent asked questions about normal distribution, like what is normal distribution in that is in statistics. Okay, what does normal distribution mean? What is normal distribution used for? Okay, and also we also have what are the characteristics of a normal distribution, and how do you know if your data is normally distributed. Okay, let's start with the first one. What is the normal or its normal distribution in statistics? So as we had said, that is the probability function that specifies how the values of a variable are distributed is called the normal distribution. It is symmetric since most of the observations assemble around the central peak of the curve. That is around this peak. Let me assume this. We have this kind of normal distribution. Okay. Yes, so you can see now, whenever you see this kind of what? This kind of shape, definitely you will know it is what? It is normal distribution. And what is it in the what? In the statistics. Basically, it shows us, okay, how our data points are what? Are assembled around a central peak, or maybe of a curve. Okay, yes, or basically it shows us that is or it shows us how a continuous that is a data set is what? Is distributed. What about what does the normal distribution mean? Okay, so in statistics and in probability theory, maybe Naomi, you can mute. Thank you. So, what does normal distribution mean? So, the normal distribution, we said it's also known as Gaussian distribution. Okay. Naomi, you can mute. Let me just mute you. Okay. So, that is in statistics, the normal distribution, we said it's also known as Gaussian distribution. Okay. And it's the most important continuous probability distribution. That's correct. As I have said, it is the the most known continuous probability distribution. Okay, because it can accommodate even decimals. All right. Yes. Then sometimes it's also known as a bell shape. What is it used for? So normal distribution is very significant in statistics and is often used in the natural sciences and in social arts to describe maybe the real valued random variable distribution, or it shows us maybe the distribution, or we use it to check the distribution of random generated values with unknown distribution. So if if those random generated values tend to follow normal distribution, definitely now we will know that that data set tends to follow what? Tends to follow a normal distribution. Okay, then we have characteristics of normal distribution. I guess we've already discussed all this. It's all about that is properties of what? Properties of a normal distribution. And on the properties of normal distribution, we are saying that it is symmetric. Okay, yes, it is symmetric or unimodal, or that is the curve. When we are talking about that is symmetric, we are talking about that is the central curve. Okay. Then that is the values of mean, median, and mode are all equal. We've discussed a lot of that. Then normal distribution is quite symmetrical about its center. Okay, that is the left side of the left side of the center of the peak is a mirror, or it's a mirror image to the what? To the other side. Okay. Yes, like the values which we have maybe on the right side, okay, they are the same values, or they are the same number of values we have in what we have on the left. Okay. Yes, that's why we are trying to say that the left of that is the left of the center of the peak. It's what? It's a mirror to or mirror image of the right. Okay. Then how do you know if data is what is normally distributed? Definitely, if you plot an histogram or you plot that is a curve, okay, it will appear to be what? To be a normal distribution curve. Okay, it will appear to be a normal distribution curve. So a histogram represents a useful graphical representation of the given data. When histogram of a distribution is superimposed with the normal curve, then the distribution is known as a normal distribution. Okay, any curve like this, you can check you will see that it tends to follow a normal distribution. Okay, what about that is real real life applications? Maybe you can go and see more. That is, I guess we had this one we saw yesterday. That is rolling over dice, tossing of a coin. That is the IQ, technical stock market, blood pressure, shoe size, birth weight, student average report. I guess we had discussed this one. Let me see if we have another applications. I can see they are almost repeating themselves. Okay, but no worry. I will also find or I will also do an example. Okay, like I will give you an example that will help you to calculate normal distribution. Okay, otherwise you can learn a lot. You can even go extra mile and learn in depth about normal distribution. Okay, for I've just given an overview of normal distribution. Any question on normal distribution? All good under normal distribution? Please go and check more on the properties of normal distribution. Okay, go and check more on the that is the properties and application, real life application of normal distribution. I will also try to source more that is examples or real life application of normal distribution, even in what, in workspace. Okay, like for example, let's assume um, you are given, maybe we are working on mobile lending loans. Okay, company, mobile lending that is loan lending that is company. Okay, so definitely we have different borrowers. Okay, definitely we have different what, different borrowers, and different borrowers. Okay, and different borrowers, we have different behavior of repayment, that is repayment behavior. Okay, we have few people who will pay within the shortest period. Okay, we also have few people who will default or who will be the last to pay, and also majority of the people, okay, will do what, will that is they will pay, okay, within the that is the stipulated loan period. Okay, majority will try to pay within the required period. Okay, so in that case you'll find that this data it will follow it, or it will kind of follow a normal distribution. We'll have few who will use maybe less time interval. Let's say on the x-axis we are talking about a repayment period. Repayment period in what? Maybe in months. Okay, there are some few people who will take few months, maybe 1 to 2 months. Okay, majority majority will pay within what? Within the required period of time, maybe 2 to 5 months, okay, and then there are few who will exceed the what? The loan repayment period. Okay, so with that, it will also tend to what? To follow a normal distribution. Okay, for that, it will tend to follow a normal distribution. So we have very many examples. That was just an example on maybe a mobile lending company. Okay, yes. All right. Okay. Good. Let me check. Can see someone. How does empirical? Okay. Yeah. So about the empirical, that is rule. Maybe you can go and study more about this. Okay. That is the 68, 95, then 99% rule. Okay. That is whereby we know that this empirical rule basically tries to that is to state that um, maybe 99.7% of your data, okay, or of the observed data follow and that follow a normal distribution lies within three standard deviations, okay, of or that is of the mean. Then and under the rule of 68%, it states that that is the data all the or it states that 68% of your data or of your observed values fall under what? Fall within one standard deviation, okay, and then 95 or yes 95% of your data, okay, follow within two or three that is standard deviations, okay, in fact two. 68 falls that is your data sets or your data values fall that is within uh, one standard deviation, for 95 within two standard deviations, then 99.7% that is within three standard deviations. But you can study about this, and then we come and brainstorm. Okay, we come and brainstorm about this. Okay, just go and research more about this, and then we'll come and brainstorm together in this class. All right. All right, then let me talk about central limit theorem in those remaining 10 that is 10 minutes. Okay, central limit theorem. What does central limit theorem mean? How do you understand by central limit theorem? Because for my case, I really understand it in a very that is in a very simple way. Okay, in a very simple way. What does or what do you understand by this term central limit theorem? Anyone? Anyone? What do you understand by the term central limit theorem? Okay, in basic, for my case, I usually start that is understand the central limit theorem. I usually start that is understand it that is in reference to population size and what? Sample size. Okay, why? Because the theorem holds that as n increases towards n, that is, as the sample size increases, okay, towards the population size, then the sample mean will also approach what? Will also approach population mean. Okay? As we increase that is the sample size, okay, towards the population size, then the mean of the sample size will approach what? Will approach that is the standard deviation, okay? And the more we will get more information, okay, about the entire population. Like for example, let's assume we have a population of 5 what? 5 values, okay? So these values are, let's say 2, 3, 6, 4, then we have 1. Okay, good. And then I just start with what? With a very that is small size, like n is equals to 2. Okay, so with that, let me calculate what we know that population mean will be 2 plus 3 plus 6 plus 4 plus 1 divide by what? 5. What will be this? So it will be 5, 11, 12, 16. 16 divided by what? It will be 16. Let me say it will be 16 divided by what? Divide by 5. Okay, which will be 3.1 something. All right. Okay, let's start maybe with with first two values. That is 2 and 3. Or let's start with 1 and 2. So we'll say that 1 plus 2 divided by 2 will be 1 point what? 1.5. Okay? I want to increase the size of n now to be what? N to be 3. So in that case it will be let's say it is 2 plus 1. Let me just illustrate it well. It will be 2 plus 3 plus 1. Okay, so divide by what? By 3. So in this case it will be this is 5, this is what? 6. So it will be what? It will be 6 divided by 3, which is 2. So you can see we've started with 1.5. We are now going to what? To 2. Okay? Meaning now we are approaching to this value. Remember that? You can see we are approaching this value. Let's take now that is the size of 4 that is values. Okay, that is a sample size of 4 values. So it will be now 2 plus 3 plus 1 plus what? 4. Divide by 4. So in this case it will be 5, 6, it will be 10. Okay, so 10 divided by 4. If 10 divided by 4 will be that is 2. That is it will be 2, because 4 divided by 10 divided by 4, it is 2. Okay, remainder 2 0.5. It will be 2 point what? 2.5. Okay, you can see we are approaching now this value. So what basically this states is that is a central limit theorem states that as we increase the sample size, okay, the sample mean approaches the what? The population what? The population mean. Understood about central limit theorem? That was my basic explanation. Was that clear? Okay, can see two have reacted. Okay, good. Now let's now go to the notes and see if that's what it says, or maybe I've I've used my own theorem, okay, to define it. Let's see if that is what the theorem is it's talking about. Okay, nice. So, what is the central limit theorem? So, in probability, that is theory, the central limit theorem states that the distribution of sample variable approaches a normal distribution. Yes, by the way, I also forget that. Okay, so as we are also increasing n, okay, so the sample of this n, all the sample data, assumes a normal distribution. As we are increasing n, all the value of n, okay, the sample data will also assume what? Will also assume a normal distribution, okay? And also, in other words, that is the mean of the mean of all the sample mean will also approach that is population mean, okay? Yes, sorry, I also forgot about that, to state that. So that is the theory, the central limit theorem states that the distribution of a sample variable approaches a normal distribution as the sample size become larger, assuming that all samples are identical in size, regardless of the population actual distribution that is shape. Okay, so this is how that is the theorem states. That is that is the sample size assumes a normal distribution, okay, or as the sample size, okay, as the sample size increases, okay, that is the sample variables tend to approach a normal distribution, okay, as the sample size increases. So basically what we are trying to mean is that um, central limit theorem states that the distribution of sample means approximates a normal distribution as the sample size gets larger, regardless of the of the population distribution. The sample size equal or greater than 30, equal or greater than 30 are often considered sufficient for central limit theorem to hold. A key aspect of central limit theorem is that the average of the sample mean and the standard deviation will equal the population mean and standard deviation as as n increases towards that is the big N. So a sufficient large sample can predict the characteristics of the population more accurately than than a small size. Okay, very correct. Remember that maybe let's assume we are studying about maybe opinion polls. Okay, like in reason, that is yesterday, we had some demonstrations in that is in Kenya. So if we were to do that is opinion polls, okay, to ask maybe if the current government is favorable or not, okay, definitely as we as we are interviewing more people, we'll get the real picture about about the government. So we can't rely maybe with two responses, okay, because these two responses might be biased. Maybe you might have come across that is the two all the two might be supporting what? The current government. So with that, you won't be able to get that is the correct feedback. But as we increase maybe the number of the interviews, okay, definitely we'll be getting more about that is the general opinion of the current government. Okay, so and if you get you are using more, that is you do more and more of the that is interviews, then you will have the real picture of all the real picture of the situation which is currently facing that is Kenyan citizens. Okay. All right. So, central limit theorem is useful in finance when analyzing a large collection of securities to estimate what? Portfolio and trades of returns, risk, and that is correlations. Then, okay, let's try and see this. It works well with what? With the law of large numbers. So, central limit theorem is often used in conjunction with that is with the law of large numbers. Okay, why? Which states that the average of the sample mean and standard deviation will come closer to equaling the population mean and the population standard deviation as the sample size grows, which is extremely useful in accurately predicting what? The characteristics of the populations. Okay? Yes, that is as the sample size increases, the sample mean and the sample standard deviation will come closer, okay, to equaling the what? The population mean and the population standard deviation. Okay, so that's all about the central limit theorem. Okay, yes, and it has very many applications. Okay, it has very many applications. Please go and check applications of what? Application of central limit theorem in what? In real life, that is a situation. Okay, all right, then I will request